Okay, good morning everyone. So we were discussing about compact operators. So today the first result I'll prove is that if T is a compact operator, then T star is compact. So I'll do it on Hilbert space. So suppose so for this I'll use a lemma. So if where T belong to B00. Yesterday I yeah let me H. This implies T star is also finite rank. So if T is a finite rank operator, then on a Hilbert space H, then T star is a finite rank operator here. H is a Hilbert space. And of course, then T star is T, so you can write this if and only if also. So this I'll leave as an exercise. So basically, you have to show that if T is a bounded linear operator whose range of T is finite dimensional, then range of T star is also finite dimensional. In fact, you can prove that the dimension of range image of T star is same as the dimension of image of T. So they are of same dimension. So now using this and the previous theorem that we did that if we have any compact operator on a Hilbert space, then uh, we can find a sequence of finite rank operator which converges to this compact operator, right? So by using that result, we can do this. So now let me write the theorem. So let H be a Hilbert space. And T is an operator from H to H. Uh, T belong to B of H. So then T is compact if and only if T star is compact. So to prove this, we'll use the lemma and the earlier theorem. So, so note that if we prove one way, then the other way is also true. If T belongs, T is a compact operator, implies T star is compact. Then if we assume T star compact, then its adjoint T double star is same as T, so that will be compact. So we actually need to prove only one way. So, so suppose T belongs to B0H. So then there exists a sequence Tn in B00H such that norm of Tn minus T, this goes to 0. In fact, in the proof, we constructed this Tn by taking the projection Pn on an n-dimensional space, and then Tn is nothing but Pn of T, Pn composed with T. So we have a sequence of finite rank operator which converges to T in the operator norm. So then we want to prove that T star is compact. So if I can show that there exists a sequence of finite rank operator which converges to T star, then T star will be compact. So now if we look at Tn star minus T star, this norm is same as norm of Tn minus T star, and for any bonded linear operator the norm of the adjoint is same as the norm of the operator. So this is same as norm of Tn minus T, and which we know it goes to 0 as n goes to infinity. So we get a sequence Tn star which converges to T star. Also by the previous lemma, Tn star is finite rank operator. Because Tn was finite rank operator. So now we get a sequence of finite rank operator which converges to T star, and we know that this B0H is a closed subspace of B of H. So therefore, if we have any sequence of compact operator, then the limit is also compact. So since B0H is closed in BH, this will imply that T star is in B0H. And the other way is T star belonging to B0H. Then this will imply that T, which is T star star, this will be in B0H. Okay, so this is then now
Sir, if we need to prove the lemma, then we'll have to show that, like for the first lemma which you wrote, that if
yeah.
T is in 00H, then T star is also in B00H. So here we'll have to show that T star is finite rank as well as it is compact. Uh, so
No, what is B00H? That is the set of all bounded finite rank operators, right?
Okay, so we won't have to worry about compactness.
So if T is bounded, then T star is bounded, that we already know, right?
Right. Okay,
So
okay.
this notation was for bounded the finite rank operator, right? So,
I see. Yeah, sorry. Thank you. Okay, so if we show bounded and finite rank, then compactness anyways follows. But okay, the definition was only bounded and finite.
yeah. So that is the thing that we want this B00H to be a subset of B0H, right? So any bounded finite rank operator is always compact. That is very easy. We proved that. And actually, this thing adjoint, like I said, that uh, we can also define adjoint if we have operator on Banach spaces. So if so on non-linear space, if I have, well, so in that case, the adjoint here for Hilbert space, the way we defined adjoint was using the Riesz representation theorem for Hilbert space. But in Banach space case, so if I have T is a map from say X to Y, then we can define its adjoint to be a map from Y star to X star, and then it also satisfies this property that norm of T star will be norm of T and those things. So it is true that if I have any compact operator between two Banach spaces, then its adjoint that will also be a compact operator between the dual. So if T is from X to Y, then T star will be from Y star to X star, and that is compact. So, but the proof will be different because you say that here we are using this thing that any compact operator can be approximated by finite rank operator, which is not true in the case of Banach space. So, but we did not discuss about adjoint in the case of operator on Banach space, so I am skipping that. Uh, but that result is also true. Thing and okay, so now I'll discuss about eigenvalues and spectrum of a bounded linear operator, and then we will see that this compact operator the, is very important because it uh, it is like closer to an operator on finite dimensional space. So even though I mean the compact operator is can be defined on infinite dimensional spaces, but we will see that the properties like the eigenvalues and other thing about a spectrum we will discuss. So let's discuss about a spectrum of a bounded linear operator. So first you recall what is an eigenvalue for an operator. So let T belongs to B of X, where X is a Banach space. For many results, we may consider only Hilbert space, but right now, let's look at X is any Banach space and T is a bounded linear operator from x to x. So recall what is an eigenvalue. So lambda belonging to f is an eigenvalue of t if, so what is the definition of eigenvalue?
Uh, that there exists some non-zero vector v such that tv equals lambda v.
Right. So I'll write this as uh, if the kernel of lambda I minus t, this is non-zero. Is it okay? So this is equivalent to that there exists a non-zero vector in the kernel, which means that there exists. So this is equivalent to there exists some x in x not equal to 0, such that tx is equal to lambda x. Right. So such an x is called an eigenvector. So if there exists a non-zero vectors which satisfies tx equal to lambda x, then we say that lambda is an eigenvalue. And this is also equivalent to saying that lambda I minus t, this is also a bounded linear operator, right? So if we look at this operator lambda and I minus t, then what can we say about this operator? This is not 1 1. Is it okay? Because if it is 1 1, then we'll get that 0 is the only vector which is in the kernel. So lambda is an eigenvalue. This is equivalent to saying that lambda I minus t is not injective, right? If my x is a finite dimensional vector space, here in fact we don't need the norm or anything. This is true for any linear operator on a vector space. We can define like this, right? So if my x is finite dimensional, then this is, so let me write, if dimension of x is finite, then lambda I minus t 1 1, lambda 1 minus I minus t is the 1 1 is equivalent to lambda I minus t is on 2. So therefore this lambda is an eigenvalue of t. This will be equivalent to lambda I minus t is not invertible if x is finite dimensional, right? So I mean this is how we define for uh, a linear operator on a finite dimensional space, that we say that the operator lambda I minus t, that is not invertible. So determinant of lambda I minus t that is equal to 0, and that is how like sometimes eigenvalue is defined on finite dimensional vector spaces. So but if it is infinite dimensional, then these are not equivalent, right? So if x is infinite dimensional, then lambda I minus t. One is not equivalent to lambda I minus t is on to. So for example, if we consider say t from say the L2 space to L2, t of x1 x2 then what can you say about this operator t? T is 1 but not onto, right? This operator is not onto O is clear because the first component is always 0, and it is 1 because if you write t of x equal to t of y, then we'll get x equal to y. So this is an example of 1 operator which is not onto. So this is called, I think we defined sometime. This is called the right shift operator. And similarly, we can consider its adjoint, which is the left shift operator. So that will be onto but not 1. So if I write S from L2 to L2, S of x1, x2, 3, and so on. This is equal to x2, x3, and so on. So S is onto but not 1. Right? In fact, if you take S of E1 100, that is mapped to the 0 vector. Right? So you see this. Let me ask, can you find the eigenvalues of T and S? What are the eigenvalues? T and S. So for T, let's look at T first. So let lambda be an eigenvalue of T, then there exists x1, x2 dot dot in L2, and this is non-zero minus 0, such that T of this is equal to lambda times x. So that will be same thing as saying 0 x1 x2 is equal to lambda times x1 x2, so on. So what will this give? So this is equivalent to writing lambda x1 is equal to 0, and then lambda x2 is x1, lambda x3 is x2, and so on. So I'll write lambda of x n plus 1 is xn for all n bigger than equal to 1. So lambda x1 is 0 and lambda xn plus 1 is equal to xn for n bigger than equal to 1. Now, can you find some lambda for which you get this non-zero x satisfying this? So first
Sir,
let's consider lambda non.
0.
So if lambda, or maybe let's say lambda equal to 0. So if lambda is equal to 0, then we get uh, xn is equal to lambda xn plus 1. This is equal to 0 for all n bigger than equal to 1, right? So this implies that uh, this x1 x2, this vector is the 0 vector. So this says that lambda equal to 0 is not an eigenvalue. Therefore lambda equal to 0 is not an eigenvalue. In fact, this you could have said, because we already said that t is 1 1. If 0 is an eigenvalue of t, then that means that uh, t cannot be 1 1, right? So t 1 1 implies that 0 is not an eigenvalue. Now if lambda is not equal to 0, lambda is non-zero, then lambda times x1 equal to 0, this will imply x1 has to be 0, right? And then we have lambda xn plus 1 is equal to xn. Also xn plus 1 is equal to xn by lambda for all n bigger than equal to 1. Because lambda is non-zero, I can divide by lambda. And now using x1 equal to 0, we will get all x is 0. So x1 is 0, x n equal to 0 for all n. So this implies again that therefore lambda is not an eigenvalue for every lambda. So this is also one interesting thing, that suppose here I was looking at this space over the field of complex numbers, then this is giving an example of an operator on a vector space over complex field which does not have an eigenvalue. Though when we look at finite dimensional vector space over C, then it must have at least one eigenvalue, right? So that follows from, because eigenvalue are just the roots of the characteristic polynomial, and if I have any polynomial over C, then it must have at least 1 0. That is by the fundamental theorem of algebra. So but on infinite dimensional, we see by this example that we can have an operator over vector space over the field of complex number which has no eigenvalue, right? So there is no eigenvalue for this operator t. What about the operator s? For s, so let lambda be an eigenvalue, then what happens? So let's try to find s of x1 x2 x3 and so on is equal to lambda times x1 x2. So this is equivalent to writing x2 x3 is equal to lambda x1, lambda x2, and so on. So this is equivalent to writing x2 is lambda x1, x3 is lambda x2, and so on. So we'll get xn plus 1 is equal to lambda times xn for all n bigger than equal to 1. Right? So now if x1 is equal to 0, if x1 is equal to 0, then xn will be equal to 0 for all n. Right? Because if x1 is 0, then you use this equation, then x2 will be equal to lambda times x1, that will be 0. Then once x2 is 0, then x3 will be lambda times x2, that is also 0. So if x1 is 0, then all xn is 0, but we want a non-zero solution to this. So therefore x1 must be non-zero if we have an eigenvalue. So if x1 is non-zero, then we will get x2 will be equal to lambda times x1, x3 will be equal to lambda x2, so that is lambda square x1, and so on. So we'll get x n plus 1 is equal to lambda to the n times x1 for n bigger than equal to 1. Right? So x2 will be lambda x1, x3 is lambda square x1, and so on. So what can you say about eigenvalues? So now can you tell
Every
what
lambda, every lambda is an eigen value. Every lambda in F is an eigenvalue with the corresponding eigenvector as like any arbitrary non-zero x1, and then we define the sequence lambda to the power n x1.
no, you have to be a little careful. So look
Oh,
at
it
the
should
space
be
where
L2.
we are considering.
Ah,
So the space was L2, right?
right. So lambda mod lambda should be less than one.
Very good. Yeah. So mod lambda less than 1. See, if I was saying that this is an operator over the sequence space vector space of all sequences, then you are correct that any lambda uh, will be an eigenvalue, right? But here we are looking at the space is only this L2 space. So therefore, you have to be careful that this vector should be in L2, right? So now this x1, x2, x3. So this can be written as now this will be equal to x1 times, I can write 1 lambda, lambda square, and so on. So when does this belong to? This belongs to L2, and x1 is non-zero, we are already taking. So that will be if and only if mod lambda is strictly less than 1, right? Because we want a summation of this so 1 plus lambda square plus lambda to the 4 and so on, that should be finite. So if mod lambda is less than 1, then that is a geometric series with ratio is less than 1 in mod, so that converges. And if mod lambda is bigger than or equal to 1, then we know that this series diverges. So therefore we get this. This is since x1 is non-zero. So therefore, the eigenvalues are precisely the set of eigenvalues of S. This is all lambda in F such that mod lambda is less than 1. Okay, so this is I just did because this is an important example to consider for eigenvalues on infinite dimensional space. Now let me define what is an spectrum. For definition, so again I'll take a Banach space and T be a bounded linear operator. Let T belong to Bx, where X is a Banach space. The spectrum of T is defined as, so the notation we will use is sigma T will denote the spectrum of T. This is equal to all those lambda in C. Yeah, also let us assume that this is a complex Banach space. So the Banach space over the field of complex number. So therefore we are looking at lambda in C such that lambda I minus T is not invertible. Okay, so here we are defining lambda such that lambda I minus T is not invertible. For eigenvalue, it was all those lambda such that lambda I minus T is not 1 1. So what we see is that the spectrum will contain all eigenvalues. So let us also give a notation for the set of all eigenvalues. So the point spectrum of T is the set of all eigenvalues of T denoted by sigma P of T. So this is equal to all lambda in C such that lambda I minus T is not 1 1. So clearly we have that this sigma pt is a subset of sigma t. Right? If lambda I minus t is not 1 1, then it cannot be invertible. So if it is an eigenvalue, then it is in the spectrum. But we may have something in the spectrum which is not an eigenvalue. Right? So because this lambda I minus t may be 1 1 but not on 2. So, I'll write this. So if lambda I minus t is 1 1 but not on 2, then this lambda belongs to spectrum of t, but it is not in the point spectrum of t. So for example, you see this operator. Uh, yeah, for the operator t. So For example, for the right shift operator, T L2 to L2. When instead of L2, I can take some other space like L infinity also, and still you will see that same thing you will get. So if I take T from say L2 to L2, yeah, there may be like some difference. For example, here like if I consider this left shift operator and the space instead of L2, suppose I take L infinity space, then can you say what are the eigenvalues? Is it still the same or different? So if it was L infinity space, then we want this vector 1 lambda lambda square and so on. This should be in L infinity, but that means that supremum of mod lambda to the n, that should be finite. So if we take any lambda with mod lambda less than equal to 1, then we have that this vector is in L infinity, right? So in that case, any lambda with mod lambda less than equal to 1, that will be an eigenvalue if we are on L infinity space. But if mod lambda is strictly bigger than 1, then this vector is not in L infinity. So it will depend on the space what the eigenvalues are. So if I taking L2 to L2, the right shift operator T of x1 x2 is equal to 0 x1 x2 so on. Then if we look at 0, this belongs to spectrum of T, but 0 is not in the point spectrum of T. Okay. 0 is not an eigenvalue because this T is 1 1, but this T is not on to, so therefore 0 I minus T, that is not invertible, so 0 belongs to a spectrum of T. Okay, so let us also define the complement of this spectrum, uh, the resolvent of T is the complement of spectrum of T and is denoted by rho of T. So this rho of T will be all lambda in C such that lambda I minus T is invertible. Okay, so now the first thing is that this spectrum of T is a bounded subset of C. So let's write this. Sigma of T is a bounded subset of T. In fact, what we will show is that lambda belonging to sigma t. This implies mod lambda has to be less than equal to norm t. Uh, the spectrum is contained in the ball of radius norm t centered at origin. It's so to prove this, we already know a result, so we can use that. So what we want to show is that, so to prove this, we will show that if mod lambda is bigger than norm t, then it is not in spectrum t. So let lambda be in C such that mod lambda is strictly bigger than norm t. So then what can I say about t by lambda? Norm of t by lambda, this is strictly less than 1, right? I mean, if mod lambda is bigger than norm t, lambda is non-zero, so I can divide by this, and we get that norm of t by lambda is less than 1. So therefore, if we look at identity minus t by lambda, what can I say about this operator?
Uh, it has a norm strictly greater than 0.
No,
The
no.
triangle.
So, is it invertible or not?
It is invertible.
Right. So, this is invertible. So, this was a problem in the midterm exam also, that if norm of an operator is strictly less than 1, then I minus t is invertible. And in fact, you can say what its inverse is. So, we also know what its inverse is, and we have a bound for this also. So let me just recall that I minus t by lambda inverse in this case will be equal to summation of, let me write it like this, t to the n by lambda to the n equal to 0 to infinity. And we also get that norm of I minus t by lambda inverse, this will be less than equal to 1 by 1 minus this norm of t by lambda. So this I can write as this is equal to mod lambda by mod lambda minus norm t. So we know that this implies that I minus t by lambda is invertible. So I minus t by lambda is invertible. This implies that uh, lambda I minus t, this is same thing as lambda times I minus t by lambda. So this will also be invertible. Right, because lambda is non-zero. So if I multiply any invertible operator by a non-zero scalar, then that is also invertible. You can write the inverse also, because I know the inverse of I minus t by lambda inverse, and then you have to just multiply it by lambda inverse to get the inverse of this, right? So, oh, lambda I minus t is invertible. This implies that lambda is not in spectrum of T. Right? So lambda belongs to the resolvent set of T. So if lambda mod lambda is bigger than norm T, then lambda is not in spectrum T. So therefore, if lambda is in spectrum T, then mod lambda has to be less than equal to norm T. Hence, we are done. So this is the one important thing, that sigma of T is a subset of lambda in C such that mod lambda less than equal to norm T. Let me write this. This is an important result. Another thing is that this spectrum sigma T, we can show that it is also a closed subset. So then it will be closed and bounded subset of C. So sigma of T is in fact a compact subset of C. So sigma of T is compact if we prove that this is closed. And to prove sigma T is closed, we will prove that this row of T is open, and then we will be done. So it will be compact. And the next important thing is that this spectrum of T is always a non-empty subset of C. So we saw that the set of eigenvalue can be an empty set, but we will show that if we have any bounded linear operator on a complex Banach space, then the spectrum is always non-empty. So that is an important result. And then we will restrict ourselves to compact operator, and then talk about what we can say about eigenvalues and spectrum of compact operators. So that we will discuss, and also we will talk about the eigenvalues and spectrum of self-adjoint operator and normal operators and so on. I think I'll stop here because we are out of time. So next thing I'll prove is that this thing, to prove that this row of T is an open subset, what we will show is that if we look at the set of all invertible operators, then we will show that that is an open subset. Right? So if I can show that, then it will follow that this thing, where row of T will be an open subset of C, and that will imply that sigma T is closed. So I'll do that next time. Any question?